Merci pour votre attention. My name is Hermann Chendjou. I'm originally from Bamendou, Cameroon, a beautiful country located in Central Africa. Cameroon is often referred to as African miniature for its geological and cultural diversity. You can clearly tell by my accent that English is not my first language. Pouvez-vous deviner quelle est ma première langue? I have earned an associate's degree in engineering, and because of my passion and fascination for electricity, will earn another associate's in electronic technology in the winter of 2019. I received both of these degrees from Schoolcraft College. Right now, I'm actively looking for a job in electronics technology or a related field. My long-term goals are to succeed in my career, attain advanced engineering degrees, and one day build a hospital in Cameroon. My motivation is very personal. My own brother suffered from epilepsy. He ultimately passed away because my family did not have the financial means for him to receive proper medical treatment. This treatment might have saved his life or at the very least prolonged it. As someone deeply passionate about science, I'm very anxious to talk to you now about Stirling Engines. They are a perfect fit for the Schoolcraft Ski Project series on the science of sustainable energy. Enjoy! Ce fut un plaisir d'être en votre compagnie. What do all the following have in common? This drinking bird. This hero engine that I made. This thermoelectric generator that is powered by the temperature difference between these two cups of water. Aha! This simple laboratory engine. This model steam engine. This Stirling engine, powered by the heat from my hand. What do they all have in common? They all run on heat, and any device that does work for us and run on heat is called a heat engine. There are many other examples. The sources of the heat that power the heat engines are critically important. They fall into two basic categories, non-renewable and renewable. Non-renewable sources are removed from the earth, for example, coal, petroleum, and natural gas, and burned to create heat. The negative health and environmental impact of using non-renewable energy are obvious. Renewable sources are not removed from the earth and are not burned. For example, solar, hydro, and wind energy. This really colorful graph from the Lawrence Livermore National Laboratory might be my favorite chart ever. Notice that the three thickest lines represent non-renewable fossil fuel. The heat they produce when burned is primarily used to generate electricity, to power vehicles, to warm buildings, and for various industrial processes. Also notice that renewable energy sources such as solar, hydro, and wind make up about 6% of the US's total energy supply. This number is growing, but a lot more science and engineering is needed. One really interesting number to look at is the amount of rejected energy, which in 2017 was approximately 68% of the total. Think about it. More than 2/3 of the energy generated in the United States in 2017 was lost mostly in the form of wasted heat. Some heat must be lost according to the second law of thermodynamics, but not 2/3 of it. This is where scientists and engineers come in. We need to make energy production and consumption cleaner and more efficient. We also need to help figure out a way to overcome the current barriers to widespread clean energy adoption. This is why I'm showcasing Stirling engines. They are simple, have some interesting commercial applications, run on air, produce zero emissions, and provide a great window into a lot of science that is common to all heat engines. This is a gamma-type Stirling engine, which is also known as a low delta T Stirling engine. Delta means difference and T refers to the temperature, so this engine runs because of a really small temperature difference. In this case, the temperature difference between my hand and the surrounding air. A gamma-type Stirling engine has two cylinders. This is the power piston, which fits snugly within this cylinder, and this is the loose-fitting displacer, which repetitively circulates the air inside. The power piston and displacer share a common volume of air. They are connected 90 degrees out of phase with each other via a crankshaft with a flywheel. The flywheel's rotational inertia makes the engine run smoothly. Without it, there would be sharp power spikes followed by weak intervals. Let's go through each step in one cycle. Step 1. The displacer rises, forcing air to the warm heat exchanger at the bottom. This is called isochoric heating. Step 2. Heat enters the air, causing it to expand. The power piston moves upward. This is called isothermal expansion. This is also the power stroke. It is where the engine is doing real work for us. Step 3. The displacer descends, forcing the warm air to the cold heat exchanger at the top. This is called isochoric cooling. Step 4. Heat leaves the air, causing it to contract. The power piston moves downward. This is called isothermal contraction. The engine is back to where it started. This flywheel plays a critical role. Its rotational inertia helps the engine move from one step to the next and provides a smoothing influence. Without it, the engine will run much rougher. That's it. This cycle is repeated over and over again. This graph, called a PV diagram, shows how pressure, volume, and temperature change during the idealized Stirling cycle and where heat enters and leaves the system. Here are the 4 steps I just outlined. This graph shows a more realistic PV diagram. The shaded area represents work done by the engine. The greater the shaded area, the greater the work output. Here's my Stirling engine running on top of a beaker of warm water. Notice that it is spinning clockwise. I'm measuring its revolution per minute with this motion sensor. Watch what happens when I put some ice cube on the top plate. All of a sudden, the temperature difference increases, and so does my engine's RPM. Now watch what happens when I reverse things by making the bottom plate the cooler heat exchanger by placing the engine on this plate of snow. Instead of spinning clockwise, it is now spinning counterclockwise. Stirling engines have been around since 1816 and are now gaining interest as part of the sustainable energy movement. They can be powered by many different clean heat sources, like passive solar and geothermal. They can also capture waste heat from automobiles, homes, and industrial processes. The more we learn about the science and engineering of heat engines, the more we can make them cleaner and more efficient. The Stirling engine provides a great learning opportunity in this area. I hope you enjoyed this video and thanks for watching. Le plaisir était pour moi. Bye bye.